So my name is Adrian, and today I have a presentation about impact manufacturing. So I will show you today part of a collaboration between Advanced Instrument and Cell and Gene Therapy Catapult. So this is because there are still a lot of challenges on AAV manufacturing. So we can still see some low process yields. Some unit operations are still not optimal. And of course, a lot of people know that the costs are still relatively high. So here on this slide, you can see a generic process for AAV manufacturing, where you start with your cell expansion, you then go into a stir tank bioreactor for production. And then finally, for the upstream, you have to disrupt the cells in order to release your AAV. So you can do that with a chemical lysis, for example. And then you go to the downstream, where you can do clarification, then followed by capture, polish, ultrafiltration, and air filtration. So today, I'm going to focus mainly on the upstream, but I will also talk about the impact it can have on both upstream and downstream. So here at Catapult, we have different platforms for different purposes. So we can do some screening and DOEs at a very small scale, so 15 ml. Then we can do some optimization at 250 ml with a scaled-down model. And finally, we can scale up to 2 liter or 50 liter. And the data I'm going to present have been generated at small scale, so 15 ml and 250 ml scale. So the process parameters used to generate those data are the following. So we are using HEC-293 suspension cells. We are doing a transient transfection with AAV1 serotype. And the media we use for this experiment is balanced CD, which has a pH between 6.7 and 7.4 and an osmolarity range between 280 to 320 milliosmol. Concerning the analytics of the experiment, so we are monitoring osmolality thanks to the Osmotech Pro from Advanced Instrument. We are also monitoring cell counts and viability, metabolite. We are assessing transfection efficiency 1 day post-transfection thanks to flow cytometry. And we are analyzing titer thanks to qPCR and ELISA for viral genome and total particle. So today, I have 2 data sets from 2 different experiments. So I'm going to start with the first one. And during this first experiment that happened at small scale, 15 ml, we went to have a look at the impact of shifting osmolality during the AAV manufacturing process. So we also wanted to have a look at the impact of using 2 ways of shifting osmolality. So using an ionic way or a non-ionic way. So you can see on the slide all the conditions we use for this experiment. And basically, we fixed osmolarity at 300 milliosmol for transfection. And we did a shift at 2 different time points, 24 hours post-transfection and 48 hours post-transfection. We did this shift at 2 different set points, 400 milliosmol and 500 milliosmol. And we did exactly the same thing with both components. So sodium chloride for shifting osmolarity with an ionic way, and using sorbitol to shift osmolarity with a non-ionic way. So before going into all the results, just as a start for the experiment, so the transfection efficiency that is determined a day post-transfection was assessed before any shift in osmolarity. So we were expecting to have a similar level for all the conditions. And you can see it's around 40% transfection efficiency for all of them. So this was as expected. It's a starting point for this experiment. Before showing you all the titer, I just want to show you some trends we want to identify from the result. And I'm going to start with the difference between using a low osmolarity and a high osmolarity in the process. So what you can see, the difference between condition from 300 milliosmol in red, 400 in green, and 500 in gray. And we can see a trend for a decrease in variability when going into high osmolarity and a decrease in cell diameter. By doing a comparison between ionic, non-ionic, and the control with no shift, what we can see is so sodium chloride in red on the bottom graph, sorbitol in green, and the control in gray. What we can see is a trend for this lower variability and a decrease in cell diameter when we use sorbitol compared to sodium chloride and the control. And I'm not showing the data on this graph, but concerning the metabolite level for all those conditions, all those comparisons, they were similar for all conditions. But having a look at the difference between shifting osmolarity at 24 hours post-transfection, at 48 post-transfection, and no shift, what we can see is like there is a trend for a decrease in lactate and ammonia accumulation when we do the shift later in the process, so at 48 hours post-transfection. So now I can show you some results about the titer, which will be of interest for most of you. So what you can see on this slide is the titer on the left for all the conditions. On the right, what you can see is a specific titer for all the conditions again. And what we saw was a trend for an increase in titer when we were using a shift with sodium chloride at high osmolarity, so 500 milliosmol, compared to the use of sorbitol. We also see a trend for an increase in specific titer when using the same condition, a shift with sodium chloride at 500 milliosmol compared to the control. And our conclusion for that was there was a significant increase in titer for a shift happening at 48 hours post-transfection at 500 milliosmol using sodium chloride. This compared to our control condition. So one more thing, what you can see at the bottom of this slide is we try to see if there was a trend with osmolarity at lysis compared to the titer. So we didn't see any trend between the titer we got and osmolarity at lysis and the specific titer. But if we only have a look at sodium chloride, we can see a trend for an increase in specific titer compared to the osmolarity at lysis. And what you can see on this slide, on the top, it's the conditions that had a shift at 24 hours post-transfection, and at the bottom, the conditions that had a shift at 48 hours post-transfection. And we can see a trend for an increase in specific titer when increasing osmolality using sodium chloride. We could not see any correlation for sorbitol, and we could not see any correlation with titer. It was only for specific titer. So for this experiment, finally, I want to show you something about empty-full ratio, because it's something we would like to increase in AAV manufacturing, increasing empty-full ratio. We want more full, obviously. So what you can see is at the left graph, the total particle for all conditions. On the middle one, you can see on the middle graph, what you can see is the specific total particle titer. And you can see a trend for a decrease in total particle when we shift osmolality later in the process, so at 48 compared to 24 hours. And if we combine those data with the previous data, what is interesting is we can see a trend for an increase in empty-full ratio when we shift osmolality later in the process at 48 hours. And this is what you can see on the graph on the right. So you can see an increase from something like 10% to almost 20% in certain conditions. So after this experiment, which was a screening and very exploratory, we did an experiment, and this will be my second data set, an experiment at 250 ml scale. So this experiment was 6 vessels and 3 different conditions, so condition in duplicate. And those 3 conditions were the following. So a control condition with our process where we control osmolality at 300 milliosmol during the process. A second condition when we decided to shift osmolality at 500 milliosmol, 48 hours post-transfection. And finally, a last condition where the same thing, but a shift at 72 hours post-transfection. And we achieve this osmolality shift thanks to sodium chloride. And it was a feeding on the bioreactor. So it wasn't a bolus addition, it was a slow feeding of roughly 30 minutes. So during this condition, during this experiment, we wanted to basically have a look at the distribution of our AAV between the cell and the supernatant. So that's why we decided to go for lysis at 3 different time points to assess this distribution. And we did it at 48 hours post-transfection, 48 hours post-transfection, 72 hours, and 96 hours. So for every time point, we did 3 different samples. So first, a standard chemical lysis of the cell culture. Then just a supernatant harvest treated with nuclease. And finally, only a lysis of the cell after being stand down. And this was in order to assess overall productivity for the lysate, release of AAV for the supernatant, and intracellular AAV for the lysed pellet. And one thing to know about this experiment is we decided to extend the production period. So, and we also decided to not use any feed. So this was in order to not affect osmolality and really having a look at the impact of osmolality on our process. So because of that, we have quite poor variabilities, especially at the end of the process. And we also had a slight deviation of one of our controls. So one of our controls had a lower cell density from the beginning of the experiment. And you will see like our control has some variability, but this can be explained because of this deviation. So concerning the titer, what you can see on this slide is from the left to the right, the 3 different time points. So 48 hours harvest, 72 hours, and 96 hours on the right. And what you can see is on the top, the 3 graphs on the top are viral particle, a specific viral particle, and on the bottom, a specific viral genome. So what is interesting is, so you can see on those graphs and the following slide, the same color code. So on in blue, it will be the control. In red, it will be the conditions that had a shift at 48 hours post-transfection. And in purple, the conditions that had a shift at 72 hours post-transfection. So on those graphs, what you can see is supernatant versus lysate. And we can see, it's quite obvious that we have more extracellular when we do a shift in osmolarity, both for the shift at 24 hours and 72 hours. And we can also see a trend for highest viral genome and viral particle, so specific viral genome and specific viral particle. So what is, I think, the most interesting is if we calculate the percentage of extracellular viral genome. This is the same color code, so for all the three conditions and the three different time points. And you can see at 96 hours, it seems that we can maximize extracellular viral genome when we have a look at the supernatant versus the overall productivity of our condition. So we are at 94, 93 hours for both conditions who had a shift in osmolality, compared to 70% for the control condition. So the variability in the control is because of the deviation I talked about. But interestingly, if we have a look at the same thing for viral particle, we have the same trend. So this time it's slightly lower in terms of extracellular viral particle. We have 84, 82% for both conditions who had a shift, compared to 61% for the control condition. But if we have a look as well at empty full ratio, what is interesting is we can see a trend for an increase in empty full ratio, having a look at empty full ratio of AAV in the supernatant. So we go to 23, 25% for condition with a shift, compared to 20% for the control condition. So all of that is still early result and quite exploratory, but we can think about the potential impact it can have on our AAV process. And basically, like we saw, like we could increase the yield of the production, and by itself, it's already like a big win, because you're gonna decrease the cost of your process. But we could also think about removing the cell disruption step, because if we get rid of the lysis, we're gonna decrease the cost. We could basically think about maximizing AAV release in the supernatant, do supervest directly. And again, it's a decrease of the cost, but we could even like think further and get rid of the clarification, do direct capture. And in this case, we use the DSP, we reduce the time, and we reduce the cost again. So all of that is potential impact. Of course, doing some cost of goods modeling would be the best, but thinking about the solution, we only use sodium chloride in order to control the osmolality, which is cheap, an easy solution to implement. It's only a feeding, and it's also like scalable if you want to scale it to manufacturing. So thank you for listening, and if you have any question.